Morning. Today I am going to be listening to some music by Jerry Steiner and Larry Brown. They composed the soundtrack to the movie Mitchell, which came out in 1975, starring Joe Don Baker. Today I found one of their albums, going to listen to it, and I'm going to review Spherical Volume Rendering Pull Request by Chris Havlin for YTIDV. I'm going to put the link to the pull request here in the chat, and then I'll give a little bit of a background with it. So, oops, looks like I can't put it there in OBS because I haven't logged in, but this is the pull request I'm going to be reviewing. The way that, and actually let me go ahead and I'm going to hop on over to the view here. Chris has been working a lot on this, and it's pretty incredible. This is a short little demo that he recorded where he's got a somewhat arbitrary grid structure. He's colored it by the refinement level so you can see where it is in the different areas. You can see that as you spin it around, it's actually doing full spherical volume rendering on it. Especially if you look out here at the edges, you see it looks like that. He also added block outlines. You can see the block outlines. This is just awesome. Let's see, here's the grid outlines. I bet he opens it up. You can see the grid outlines, and that matches everything that's going on there. This is just really awesome stuff. The tricky part with this has always been that, well, and you know what, let me do a brief example of why this is the case. Oh my gosh, it's so cool looking. Spherical volume rendering has always been a really tricky thing in YT, and it's one that has been on my list of stuff that I'm interested in for a super long time. And today I am excited to get to review this work that Chris put in. So let me do a brief little diagram. Typically, the way we would normally do volume rendering inside something like YT, typically you've got multiple grids and they might overlap. Here, let me do a diagram of what this might look like here. And each one of these has individual cells in it. Let's draw these as grids. So you've got something like this, and then oops, I'm using my Blender keyboard shortcuts here. And then, out here, there's grid lines like this. They're usually, in AMR, they're twice as big, or, some factor as big in the coarser areas. So something like this. Oh, and this is where it's going to get all messy because I didn't figure it all out properly. Anyway, something like this. This over here doesn't quite work. I guess I could shrink this and then it'll work. Yeah, there we go. I'm getting really caught up in this when I probably shouldn't be. almost done. And so what we do in YT, if we've got a ray passing through the domain, you've got a bunch of rays for volume rendering, is we accumulate values along the rays. And typically in YT we do that by decomposing into individual grids, or into individual blocks. And so we separate this here. Let's do that in blue, make it extra thick. And then we would separate it here. And this would cut it up into, and I think this is roughly how it would look. It would cut it up into 4 bricks. It might only cut it up into 1, 2, 3 bricks, but it might cut it up into 1, 2, 3, 4, depending on the order of dimensionality and constructing it into the KD tree. And then we would just ray trace across each one individually. And so that would give us a very straightforward thing to do. We know how to trace rays across these different things. Now, if you're dealing with curved lines, and so let's say we're dealing with, let me go back to our standard color here. If you're dealing with spherical coordinate systems, things get a little bit trickier. And I'm going to demonstrate this using just cylindrical, but in 3 dimensions it actually gets a lot harder as well. Let me stick one here in the middle. That doesn't look good. Like that, right? And so then we've got rays like this. Right? Sorry, not rays, grid lines like that. And I should probably just extend these all the way, and that way they'll go through the center. And so here, if we've got a ray passing through the domain like this, for instance, it's not as trivial as here. So here you can split it up into its motion across each of the 3 axes, if it's in 3 dimensions, or 2 axes if it's in 2. And then you just do a parameterization. Oh, how long does it take to cross the x planes? How long does it take to cross the y planes, et cetera, et cetera. In 3 dimensions, if you were doing that the exact same way, it would be a lot trickier, because you'll see, among other things, it doesn't track the parameters exactly the same way. For rays like this one, if you imagine you've got a radius grid, so R is in your index, I, J, or 0, 1, 2, for instance, or I guess 0, 1, 2, 3. In R, it doesn't monotonically increase, whereas here it monotonically increases or decreases in each of the 3 dimensions. Whereas here, as it gets closer to the point of closest approach, once it gets to R equal to your impact parameter, it switches direction. And so combined with the other oddities in the fact that the parameter is different for parallel rays, so the delta T for crossing theta and phi grid cells as well as R changes based on your current position along the parameter, it becomes a lot less straightforward to compute your order of operations, or order of cell traversal. The other thing that really hits home is that the distance that it crosses can be non-trivial to compute. Well, it's not that it's non-trivial. It can be annoying to compute. It involves things like square roots, and it can involve inverse trigonometric functions and whatnot. So that becomes a little bit tricky. So being able to do this is awesome and hard. And I am really, really delighted to be able to experiment with this. So I am going to list the pull requests here. I'm going to check out 159. And then we're going to take a look at it and provide some comments and feedback. All right. So let's see. Looks like there's a lot of good documentation. Let's take a look at the examples. Let's run this. Oh, dang. All right, Python. Looks like I upgraded NumPy. Here, let me do this. Let's force a recompile. NumPy 2 has been a surprisingly straightforward upgrade in almost all cases for me, but sometimes it grabs me with things like, oh, I need to recompile or something like that. I gotta say, this album is not what I expected at all. Right now it's a John Denver song. Okay. There we go. All right, so let's take a look at this. Element 1 block rendering. Sample factor of 25. Okay. Something looks different in mine than it did in Chris's. I wonder if that's, yeah, it's the sample factor. Now cranking that up to 50 improves things, but it definitely has a very angular dependency to it. I wonder if, let's go back here to his diagram and see if I can make it look identical. If I can, and it's a, let's see, this doesn't show my, this one doesn't actually show the sample factor, and I think it's exaggerated by the fact that I'm only rendering a portion of it here. So we'll try again. This one, this is what it should look like, I think. Let me see if it shows here the sample factor he's using, and if I can duplicate that. Oh, there we go. All right, play. No, mine doesn't have the full. Oh yeah, he doesn't open up block rendering to see it, so. Let's see, the depth buffer is interesting. Okay. All right. Yeah, these edges, I'm not seeing this same smoothness that he is. There must be a parameter that I'm not doing. All right, let's take a look at examples. Let's do it without refinement. This looks more like the one he had. Yeah. There we go. I love those curved lines. Algae. All right. All right, so let's go back and do a little code review here. Let's take a look. All right. Let's go here. Let's take a look at the files changed. We're going to do a little code review. Okay, yep. Coordinate utilities. Support for volume rendering. Gosh, I like this. Yep, Moody Blues cover now. Texture maps are stored in native coordinates. Yep. All right, so we've got some. Yeah, this is really good writing. I've always been impressed with Chris's writing. Mixed coordinate bounding box child class. Oh, I like that. Get Cartesian B box. Yep. Yeah, block collection should be updated. Okay. You update the rendering pipeline, adding support to the rendering pipeline. So this is actually even further than I thought, because he's including additional stuff to support other types of geometries that have not yet been implemented. That's wonderful. Okay. Yep, got your example. Oh, I see what was going on. He actually implemented more than I saw. Yeah, there we go. Okay, so let's do domain. We will do whole. Oh, man. Oh, gosh. I'm so used to examples being so bare bones when I write them. Okay. Let's see if I drop the sample way down. Yeah, ah, there we go. Oh, yeah. Actually not that bad with 33 even. Okay. So that's spherical AMR rendering with refinement is... so maybe the spherical AMR rendering should actually be called... what's it called? Should this be AMR in the file name or Unigrid? Alright, start that review. Okay. Let's do a domain here of whole. That looks exactly like what he had done. Now, oh, that's interesting. So when I zoom in, note that the ray resolution naturally gets higher because of the, so as I zoom out, it gets worse at fixed sample size. Okay, that makes sense. All right, looks good. Okay. Yeah, this all looks, I actually don't, that this is, let's see, looks good there. Yeah, I think runtime error is the way to go with argparse. Oh, oh boy, one of those days. Very sleepy. This is definitely getting me up and interested though. Okay. Okay, he's got some fields that are pretty cool. Rev, yeah, all right. Geometry spherical, axis orders, ax order. Where is ax order defined? Okay, I guess there. All right, let's go come on down here and take a look at coordinate utilities. All right. Oh, CDEF returning a tuple. Interesting. Now, I doubt that this, I mean, there's no way this is a well, is there? But I doubt there's a performance error here, or performance issue. I'm curious, though, how it packs those. So let me run. Let's take a look now. Anywhere that it calls the, oh, look at that. Okay, so it creates the F0, F1, F2 fields inside a temp. I did not know that. That's awesome. All right. So now, in general, this probably doesn't take up very much time because it doesn't get used very much. I'll leave a comment here. Okay, mixed coordinate B box, pos 0, pos 1, pos 2, D pos 0. Okay, so this gives you back, okay. And then this is the specific implementation on that class. I'm not sure you need to define this. If it's an identical signature, I'm not sure that you do. So let's take a look down here. Coordinate utilities PYX. Let's load that diff. I think it should be a big diff because it doesn't, because it didn't exist before. libc math, good. Oh, good, atan2. Love some use of atan2. Square root of x times x. A cosine z over r, atan2 y comma x. Yep, good. atan2 returns negative pi to pi. Adjust to 0. Okay, yeah, that still needs atan2. Cartesian spherical. SHP here. Okay, that's zeros. Oh, I didn't know you could do that. Interesting. Yeah. Okay, x1d size. All right, so here it just calls it on each one. Take a look at that one. Okay, so this is a Python function. These three things are not time sensitive. No GIL, not a big deal. Reshape, not a big deal. Spherical with Cartesian, and then down here. Wow, not a single bit of yellow on any of this. Wow. Okay. Reduce two bounding boxes. Find the effective bounding box given two others. So the minimum of along each dimension minus the cell size. Okay, so that's the xy0. You can subtract. Okay, so these are the two different bounding boxes. So the left edge of one, left edge of the other, right edge, right edge. Okay, the XYZ is the mean. That, the DX, okay. Yeah, that looks right. Yeah, CDEF int ndem equals 3. This is good practice. It shouldn't cost any extra time. And in principle, it makes it much clearer the number of dimensions, that's because of the number of dimensions, not because of some other set of values. Spherical mixed coordinate bounding box. If dpos 1 is less than max angle. Okay, so this is a free parameter. Let's see this. The element will be recursively divided. Oh, so cool. So this is for each element. Additional first sample point. This is for the get Cartesian bounding box. So that should allow it to work. So I wonder where did point 2 come from? Second sample is dpos 1, 2. Okay, so that's 1 divided by 2. Okay, so this is the left edge, right edge, and then, yeah, you reduce the 2. Dpos 2 greater than or equal to. Okay, so if it's bigger than the maximum angle, then it does a first sample, second sample, but this does it for each left and right. Get the Cartesian bounding box, initialize left to right, okay. Negative inf, ooh, inf, those are always fun. Eight corners, half of the various things. Yeah, so I think this is unavoidable. I wonder, here, this is float, but I guess it doesn't matter too much because it'll be upcast here since this is always going to be 0 or 1. If the polar angle phi spans, oh yeah, that's hard. It'll miss the cusp. The phone does check for when, so when the edge aligns with phi is equal to that, but it doesn't handle elements spanning periodic boundaries, which is kind of to be expected. If they span whole quadrants, I mean, in those situations, it's really better to do something very purpose-built for that. Like it can be handled in a much more. Oops. All right, let's see. I need a new piece of music. It can be handled by more purpose-built things that are, because in that particular situation, it's more likely you're going to be dealing with fairly low resolution data as an example. Let's see. I think I'll go ahead and I'll listen to a little Oceanator because I gotta get off in a little while. So here, if it's left, right, so there it spans it. Yep. That looks all right. Is this a def? Yeah, it's a def. So the function overhead is going to swallow up whatever that expenses anyway. Yeah, failure plus equals I result. Okay. Cartesian bbox edges. This is quite elegant in how they do it and how he does it. All right, so now the scene component. Update geometry preprocessor directive. So if the data geometry changes, which it likely won't, but could actually, I suppose. Okay, so here it sets the attribute, the shader tuple. Yep. Nice. All right, so here, yeah. Okay, so it checks whether or not it can do the various different shaders. That looks right. Imports this on demand, just like before. This following only works for Cartesian data. I think we want to get rid of that, because I think that is not true anymore. Okay. Oh, this is super important. Good catch. Okay, yeah, so the uniform should be for the entire domain. Oh, here we go. Okay, so this is a fairly long set of functions, but I don't know that we should remove it or refactor it at this point. Okay, so this calls its various functions. This doesn't live forever. Domain width. Outline type is blocks. Okay. Yep. I'm not a huge fan of linspace as opposed to mgrid, but you know, whatever. Um, add curve. Oh, right. Yes. Wow. Get camera for geometry. This is very clever. Managing stuff in Cartesian coordinates when it is all done internally in spherical. Okay, native. It's non-Cartesian, so this will get compiled in and out at shader time. Oh boy. Can this be represented in? Import numpy as np. F equals np dot float 64f. Let's see. v64 v32 equals np dot float 32f. Oops. Yeah. All right. I do think it's appropriate. I mean, this is fine. So we got our spherical coordinates, uniforms. All right, non-Cartesian left edge. Yeah. All right. So here's our Cartesian b-box max width. All right, and here's where it's computing the r squared square root v out IDR. Yeah. Okay. Oh, is this more efficient? It doesn't matter. A cosine, a tan. Is it just a tan or a tan 2? Huh. Interesting. 5 less. Yep, does the exact same stuff. Get the texture offset. This I don't think is exactly right. Well, no, it is. That's fine. Is it? Let's see. Can I do ones? Okay, so that's maximum intensity. Projective integration. So this is where you can pick out some of the artifacting. The maximum is the easier one to do because you should get limb darkening at the edges, which we're seeing. The maximum should always be at the very center, and it should be roughly equal to 1. Now we're seeing some distortion here, but it's not bad. It's pretty good. I am going to leave a comment here. So let me go ahead and screenshot this. Okay. Now let me do this one. Okay, spherical VR on axis. go ahead and I'm going to attach this. Let me preview. It looks good. Okay. To be clear, I mean, these artifacts are not deal breakers, but I'm wondering if this is a source of the artifacts, and if we could use more precise values to compute. Okay. Texture range in native coordinates, yep. Within element, true. Okay, so this is where it should all be. Nice. The coordinate system is good. Good pi testing. Oops. Alright, I'm going to finish my review and then move on, see if I can get anything else done. This is amazing. I've left a few comments, including one about possible artifacts. I think it's generally good to go. Oh, wow. I wonder if I can get, how do I, let's go ahead and delete that message in the chat. So, spammy spam. Okay, now let's take a quick look at some of these other pull requests before I gotta go. Display camera dictionary, update, use only intersection. That's a work in, or a draft, a work in progress draft. Print the camera state, copy that. Oh, that sounds like a great plan. Here, let's watch the video. Yeah. Get the scene, camera, print camera to console. Nice. So you can do it like it says from a script. Great. All right, let's take a look. Yeah, that works. I would have also accepted pprint. So let's go ahead and merge this. This PR adds a couple attributes to the block collection. Grid IDs that contain all the blocks. I thought we had that. Oh, maybe not. Grid ID list. Grids by block value. Okay, that probably works. Grid positions. Yeah, that's that. Index grids GID. This check that you don't need to do a ID offset for these. Sometimes we do for grids that are indexed by 1 as opposed to indexed by 0. I suspect this is fine, but I think we need to double check. Okay, I'm going to mark this as need to check the ID offset and fix a conflict, otherwise mergeable. Okay, let's see, what else was there? Now, he mentioned inside the spherical volume ranging refactor that there was another PR to look at. 64. Once FA1 is fixed. Okay. Okay, and that brings me up to just about where I need to stop for the day. So that was fun. Got to do some really cool spherical volume rendering. Got to read some awesome code from Chris and do some YT work. So that was a great day. I hope all you folks out there, let's see how many, all one of you that may or may not really exist, have a good day as well. Try to, hang in there. And all right.